I will maybe try to do a bit more of the details of what Lyapunov exponents and Lyapunov vectors are. And so bear with me for gaps that I will fill up on the spot as I go, and let's see how it goes. Yeah. Okay. So, but before I get there, because the first thing was we talked a bit about the difference between aleatory and epistemic uncertainty. So I will give a brief, so to say, at least one viewpoint of how epistemic uncertainty can play a role in dynamical systems, and what kind of models can be created for epistemic uncertainty, or what's the basis, basically something like theoretical basis for creating models for epistemic uncertainty. Parts of the system that we don't know, how do we model those, or how do you think about modeling those? And so that's basically at least the first part, and then I will go to Lyapunov exponents. Okay, so epistemic uncertainty essentially means that we have a system, and I will think of dynamical system. So here is how I want to try to use colors and see if that works well. And a dynamical system where we have a system that we are trying to model using a certain approximation of the dynamics of that system. The example that I gave were things like clouds, for example, traffic flow. There are parts of the system that we don't know, and so on. Right? So, and this I will do in discrete time. So here is time will go this way, and the system. So this is the actual system. I'll denote by. Let me keep the symbols the same as what I have here. Yeah. Okay. So WK. So the system is evolving in time, and we have some assumption always in these kind of systems that there is a connection between the system at a given time and the system at next time. So for now, I will simply take it to be something like what is called Markovian assumption. That is, the system at a given time depends only on the system at the previous time and not on the past history. If that were the case, there are ways to convert that kind of system into a Markovian and so on and so forth. But for now, this is pretty common, for example, for all physical laws. All physical laws are based on this assumption, and that's partly why you need momentum. If you don't include momentum, then the system is not Markovian, only for position, for example, and so on, right? So, so this is not a very uncommon situation or uncommon assumption or unreasonable assumption to make. Okay, and there is possibly some, and there is a functional dependence of the system at a given time on the previous time. So this depends on what this basically means is, let me start writing down the equations on the other side, where we have basically GK of WK is equal to WK plus 1, and so on and so forth, right? So this is the part that we do not know. We do not know what exactly this functional dependence is. And that's part of this epistemic uncertainty. So what we create is some model for this system. So this is the actual physical system. The Earth with all its glory, complexity, ice, ships, you have clouds, humans, unfortunately, and so on and so forth, right? Okay, sorry, I guess I should have put dot, dot, dot here. It's not that you start at time k, so these dots go back in time. And we have a model, so I will call the model system, for reasons I will explain in a minute, as WKT, WK plus 1T, WK plus 2T, and so on. And the model of the system, just one second, the model of the system also, we want to have the same property as what we assume about the system as being Markovian. And so we will incorporate this assumption. Yes, question? No, not necessary. It can be identical. It can be exactly the same. So for example, if this were, say, the pendulum system, then gk plus 1, gk plus 2 will be all the same. Time autonomous dynamical systems will have the property that all the gk's are the same. If the system is non-autonomous, then the gk's will change. For the Earth system, for example, if you think of the Earth as the dynamical system of interest, then, for example, the gk's will have a time periodicity of about 12 months. The solar radiation has a periodicity of 12 months, 1 year. And so these gk's will now be, they will be the same for 12 months and then again repeat the same for 12 months and so on. So it depends on the system. They need not be time dependent, they may be, they may not be. This is the sort of a general way of doing it. Yeah? And so the same thing will reflect in our description of the model of the system as well. And so actually let the model state space. Okay. So here is a concrete example. Let's say we think of the Earth as our system of interest, which has clouds. The model of the system is the model without clouds. In fact, there are such models, right? In the first weather forecasting models that people developed did not have any representation of clouds whatsoever, pretty much. They slowly started developing more and more and so on. There are various different approximations that can go in. For example, this could be a full three-dimensional system, and this could be a two-dimensional model representation of that system. So whenever you talk of, let's say, two-dimensional fluid flow, like what Jim was talking about yesterday for at least part of his talk and so on, that's an approximation because the real system is indeed three-dimensional. So we are basically dropping certain parts of the system while doing a modeling exercise. And in some sense, this is, we expect that there is some relationship between the model of the system and the true system that we have. And so there will be ways to at least conceptually relate the true system to the model system. And that's basically what this physical modeling is about. And I will denote this by pi, which is a projection. So this will be a projection in the sense that a projection does not have inverse. So, well, the simplest example of a projection is if you have R2, a point here, x comma y, of course, a projection onto the x coordinate going from 2 dimension to 1 dimension is a projection, and clearly you can see there is no inverse because for every point here, there are infinitely many points in the original space and so on. So projections don't have inverses typically, and that's what will happen in our model system, that the projection will not have inverse. That is, given the model state space, we will not know exactly how to get, even conceptually, what the actual physical system is. And this is pretty much always the case. Every model, almost, well, okay, I think every model maybe, really is a limited representation of the true system, and hence going back from the model to the system is not possible. And this is something that's always common. Because of this, what happens is that even if we want the model system to have this property that the system at given time depends on the system at previous time, it in fact will not be the case. As I said, if, for example, so this was the wish that we had, but it actually does not apply. Why? So let me put a different type of arrow. I don't know, something. Here is a trivial example, or not trivial, but example that is not used in practice. If this is the pendulum system, consists essentially, we know what the laws of that system are, Newton's laws, if you give me momentum and position, that is the angular momentum and position, then I can get the system at next time, and so on and so forth. If I were to model it simply by looking at the angle of the system, then it's not Markovian. The angle, purely the angle at a given time, does not depend only on the angle at the previous time, and so on. And so this Markovian assumption will not in fact be valid for that kind of, possibly valid for that kind of system. So that's a really bad example. That's not what we usually do. What we usually do is that, so what I just said is usually not, we don't go to such extremes as to really drop parts of the system. So they are the relevant parts of the system, in this case, momentum. Usually the parts that we drop is something about which we don't know. The example was clouds, for example, right? We simply do not know enough about how to model clouds, so we can't include them in the model because we don't know how to write equations for those. Okay, so that's basically what I have in mind when I try to write this. And then there is, so this is the true dynamics. This is a representation of the true system in our model state space. And then what we actually simulate. So our, so to say, the numerical, let me for now write it as a numerical, but it can be analytical solution as well, numerical model evolution. And just what's the symbol I use? UKD. Okay, so A plus 1. And think of this as, for example, I'm taking, say, the Buzynek's equations that Jim wrote down yesterday and solve them on the computer or solve them analytically if I wish. So numerical, that's why I said it's just a placeholder, but some appropriate way of solving the model dynamical system that we have with us in place. And this we know exactly how to do because that's exactly the numerical model that we develop. And so the connection between this model system at time k and the one at time k plus 1 is something that we construct, and hence we have available with us what this system does. So in this whole board, essentially all we have with us right now, or we will have with us, is all of this is actually unknown. And this is all we have constructed from the physical system, or rather, given our understanding of the physical system, we construct a model state space on which we build a dynamical model that we can actually evolve forward in time. Now, so what's the connection between now all these pieces? One, as I said, is there is always a projection because we always represent a part of the system. What about the true representation of the state of the system in the model state space and the one that we actually simulate? So these two will not really be equal necessarily, right? So these two may not be equal. This is the equal to sign put on its head. These two are not equal, sorry. The equal to sign put on its head looks a bit weird, but I just said it in words, so hopefully you understand what I'm trying to say. And in particular also there, sorry, I guess I needed one more layer. That's why I had this space, extra space. So okay, let me put I want the extra space because I need to put something else here, which is, look, this is a state space, this is a representation of the system in the model state space. In principle, if we have access to this object, we can go forward in time using the model F. And we could get something like, well, I guess this is basically Fk of W k plus 1t. And so on and so forth. So we could possibly get forward time evolution of the true state, or of the representation of the true state of the system in the model state space. That's why the T. The T here stands for truth. If you believe in truth, use it. If you don't believe in truth, just use it as T. Uh, it's a representation, ideal representation of the system in the model state space. In principle, we could use the model to go forward in time. Because we have dropped certain parts of this dynamical system, the true representation of the system at time k plus 1 is not going to be equal to the time evolution of the true representation at time k going forward with our limited model that is not equal to gk. So fk is never going to be equal to gk because we do not know the full states space. And hence, these two are not going to be equal to each other. These two are not going to be equal to each other. And what we really want to, the modeling exercise reduces to trying to decrease two things. One, trying to make these two systems as close to each other as possible and trying to decrease the discrepancy between the true evolution of the dynamical system and our model evolution of the dynamical system. So that's what we eventually need to aim for in order to reduce the epistemic uncertainty. And this can, so once I have written all this down, or rather drawn the diagram, converting this into equations is pretty straightforward, which is as follows. So we'll assume that gk exists, but we do not know. We assume that pi exists, but we do not know. Fk is something that we explicitly know because that's what we construct as the model of the system. And then given all this, here is how it looks like. So let me not get the equations wrong. So this, how do we account for this discrepancy? The way, or in equation, the way it will look like is as follows. So W, I'm just going to now blindly follow the arrows in this, right? So W k plus 1t is, what is wk plus 1t? Is the projection of the system at that time. So it's pi of w k plus 1. Is it better to start here? Yeah, I think that's okay. And which is itself equal to pi of gk wk, which is a true time evolution of the system from time k. And now I add and subtract something that I know and don't know. So if I do fk of wk, fk of wkt, so that I can apply plus, so this is something I know how to evaluate, plus add and subtract the same term. So pi of gk wk minus fk of wkt. Okay. And essentially, so this is basically fk of wkt plus delta, and recall that this wkt is basically pi of wk. So whatever is inside this parenthesis is a function of wk. Pi applied to gk of wk and fk applied to pi of wk. So this is a function of wk. And written in functional form, this basically looks like this, that delta is essentially equivalent to pi gk minus fk pi as function. So this is composition of functions. And this is what is called model discrepancy, model error, epistemic uncertainty, and so on and so forth. So the mathematical representation of epistemic uncertainty or model error in the case of dynamical system arises from two facts. One is the projection, what parts of the system we are leaving out, that's the pi. And what's the discrepancy between the true dynamics and the model that we use for it. So it depends on pi, the projection, the gk, and the fk. If pi were identity, so pi goes away as an identity operation. Fk is actually equal to gk, then this is 0, and there is no epistemic uncertainty, there is no model error, and we have a perfect model, which is a oxymoron. Such a thing does not exist, but anyway. Okay, so that's one part of how do you represent uncertainty. I will not go through. So now what do we do if we have, if we know that there will be epistemic uncertainties in the models of the system? How do we try to utilize those? One common way to do this is to say that, well, maybe try to represent this by some stochastic terms. That is, if we can understand statistical properties of this epistemic uncertainty, then we can build stochastic models of the dynamical system where this now will become a stochastic input to the model that we have. So we start trying to build a deterministic model because of epistemic uncertainty. If we have sufficient statistical understanding of the epistemic uncertainty, we can try to build a stochastic model. And this is done in many contexts. For example, something like stochastic homogenization methods and so on and so forth is one way to try to achieve this. But so even if we start with a desire to have a deterministic model, we may be forced to actually use a stochastic model eventually at some point. And this is not uncommon at all. Okay, the second reason for using probability distribution statistic and stochasticity will be tomorrow, which is what happens when you try to actually simulate these models. Okay, so will you have access to a laptop that you can get tomorrow with Python installed? How can I share these things? I guess I will. Okay, I think no, so what I will do is I'll send you a link and you can just share it. You have the list of participants and all that, right? So somebody has it. I'm assuming somebody has it. So I will then share the link to the Python notebook and the packages that are needed. Apart from all the standard ones like SciPy, NumPy, and so on and so forth, the only other one needed was JAX, but you may already have JAX and so on. So I'll list out all those things and just share the link with you, and then we can, yeah. So okay, so the other incarnation of where stochasticity comes in will be tomorrow in the actual. So it will be good to. Okay, so this is what is called. I said it. I didn't write it down. This is the model error. It's so commonly used that I use the term error even if I don't really like the phrase error. But anyway, and this is basically where it comes from, the epistemic uncertainty. Yeah. Okay. Example would have been good, but examples are really difficult to come by in this case. For that, we really need to build models and so on and so forth, which is not exactly what we are doing, and too short a time. A longer tutorial is what will be needed for that. But anyway, yes, question. Yeah. Yeah. Thanks. Somebody is paying attention. This is K. Yes, that's right. Yeah. And this is K plus 1. Yeah. Okay. Yes, thank you. Yes, that was a typo. And yeah, that went in here. This was the FKWK. And okay. A fun aside, not fun, but okay, slightly bit more complicated. I can erase these, no? I don't think that you already have these. So if we do not know what the true system representation of the system dynamics is, but we want to find a actual good simulation, so to say. How do we get to this if we don't know what this is in the first place? What's the connection between the true system and the actual model simulation that we want to build, that we want to do? How do we connect this piece, which is what we can do, to this piece, which is the true system that we may be able to observe, without actually knowing, which we cannot know, the true representation of the system? So this is never known. This is not known, but can be observed. So there are measurements of this system that may be available. So even though the system itself is unknown, the connection between this and this is only through observations or measurements of this dynamical system. And maybe I'll just do that little. So that's not quite exactly like the okay, again, it is related to the epistemic uncertainty in some way, not explicitly, but here is that little piece of the diagram now. And that little piece is not that, if you like commutative diagrams or non-commutative diagrams, you can try to do this into a nice little diagram, but anyway. Okay, so what are the observations of the system? The observations of the system will of course be, again, we assume that the observation of the system is in fact dependent on the system itself. Well, it better be, otherwise. And one additional piece is that the observation of the system at a given time is dependent on the state of the system at that time. That's an additional assumption, not unreasonable, has to be justified. It's not explicitly, it's not always necessarily true. So there is some function, I will call it H, okay, again, symbol. What's the symbol? H, K, C, I don't know why it is. So H, K, C, why C, I don't remember. That gives us the observation, and this is W, K, O. So the observation of the system at time K is only a function of the system at that time, and that function is HKC. Where can this fail? For example, we are trying to observe the sea surface from a satellite. The light takes finite amount of time to go from the sea surface to the satellite. Okay, that's actually a very, very small fraction of a, I don't know, what second, nanosecond, millisecond, something. And so that may be neglected, but there's a time delay. Such time delays can be significant at times. There may be cases when the time delay between what you actually get, how you get the observation of the system that you want to observe at that time may be significant. This time delay between the satellite observation and the sea surface is maybe completely negligible in this context, but there could be contexts when it need not be negligible, in which case we have to call into question this assumption of the observation at the same time depending on the state. Or the usual way of doing it is to expand the definition of the system itself to include whatever is causing the time delay and so on and so forth. But anyway, okay. So you have to keep in mind that this is something that we need to think about, right? Okay. What we, again, as I said, we don't have access to this. What we want to try to do is to figure out how the true system, or rather the model system, is related to the observation itself. And so this will be an arrow going from the model state space to the observation. So what we can build is, how does our model state space relate to the observations? Here is a concrete example of where these two need not be equal. Again, example of this, satellite observations of the sea surface. We are observing from the satellite. The true system contains clouds, and the clouds affect the observation of the sea surface. So this operator will include the dependence of the observation on the clouds, which are part of the true system. Our model is the model without clouds. There is no way we can represent how the observation is affected by clouds in a model that in fact does not even have clouds. So the observation that we build, the observation operator, the way observation is related to our model state space, the way we build this HK will simply have no representation of the clouds again. And so these two will not be equal to each other. Just like Fk and Gk are not equal to each other, Hk and Hkc are not going to be the same. And so again the same thing, the discrepancy between those two is what typically will be called observation error, and that will be a part of both the epistemic and aleatory errors. So here is so to say the slightly longer, only slightly longer. So what I've left out is maybe as follows, that I don't know what to put here, but some other arrow or something. There is a little bit additional, which is that when we get the observation is not just affected by the system, but something like the noise, the measurement noise. What I call aleatory uncertainty, measurement uncertainty, and so on and so forth. And this will be indicated by, say, epsilon k. Right? So this arrow is weird because it's weird in the sense that I want to eventually add the observation without noise and noise together, and I don't know how to represent it in a picture, so I just drew some weird looking arrow as a placeholder. Okay, so the corresponding set of equations for the observations would be of the following form. WKO is the same bit. This is what the observation would be without the measurement noise or without the aleatory uncertainty, but there is the epsilon k added to it. Yeah, I'm right now assuming a additive noise. If you take multiplicative noise, the same similar kind of manipulation can be done. Just gets a little bit more complicated, so not really necessary for now. Already sufficiently complicated. Okay, and this, we do the same thing. What we know is HK, what we know is W, or what we want to know is WKT. So this is equal to HK of WKT plus everything else. And everything else will now depend on, again, WK. So here it is. So HKC WK minus HK of WK, which is exactly this term, sorry, WKT, plus epsilon K. And the same thing as earlier, this is HK WKT plus epsilon K WK. Oh, well, actually, sorry, epsilon K, what is something? Epsilon K O, E plus epsilon K. This is a function of WK because WKT again is pi of WK. Right? And so the epsilon KE is exactly like the previous case, simply equal to HKC minus HK composed with pi. Right? Exactly in parallel to the model error or epistemic uncertainty that I wrote down there. So this is basically the epistemic uncertainty or the model or the error, epistemic error, in the observations of the system along with the actual measurement or aleatory uncertainty in a system. And so these two combined together will be the observational error. I'm running out of space. So that will be the observation. Again, I'll use the term error. Really, uncertainty is a better term. Observation uncertainty is a combination of the epistemic uncertainty in the observation and the aleatory uncertainty in the observations. Okay. So, so how do we want to actually then eventually use all of this? Well, yeah. So that's I guess so that at least gets us part of the way to try to relate to this dynamics finally, right? And the whole so say at least one of the ways to try to relate these two will be to say, can we make so methods to minimize, oops, the discrepancy of the dynamics that we actually simulate and the dynamics of the true system is essentially what the main aim of all of this eventually, all of this modeling exercise eventually will be. And I'm not going to discuss all of these details, but just how to build models to incorporate epistemic uncertainty and aleatory uncertainty together into one, so to say, conceptual framework. That's basically what this boils down to. I should have written down. I will then put the thing. I will put a link to the paper here. This is by. This is in the paper by something like 1997 or 98, approximately. And I will put the exact reference in the in the link I will share with you later. The paper is quite long. It goes on to actually talk about the methods to do this and so on and so forth, which I'm not going to get into. But this is just the first section of the paper that discusses all of this. And if I remember correctly, I tried to keep the notation as close to that of the paper as possible, I think. But okay. Anyway, okay. So that's about the epistemic and aleatory uncertainty. Now about the growth of uncertainties because of dynamics. And that's where we need to talk about stability and instability. So to say the first 3, 4, 5, I don't know how many classes in a typical dynamical systems course. How many of you have done at least some course either in dynamical systems or nonlinear dynamics? 1, 2. Okay, so most of the people. Okay, great, perfect. So this is a quick revision then. This is not going to be exhaustive lecture as such, but a quick revision. So let me erase this. I'm not going to talk about this. So, but that's eventually the aim of this whole exercise. Okay. So what do instabilities have to do with uncertainty? For that, we'll need to understand what do you mean by instability and how do you mathematically characterize instabilities. So here is the simplest, so to say, the starting point, the basic starting point for general linear systems. So for a linear autonomous system x dot equal to ax, dx by dt. X dot is dx by dt. And in Rn or the following fact, which is I guess basically a theorem, I will simply state it. Let be eigenvectors for eigenvectors of A. Sorry, the index I and this I are the different I. Okay, I think anyway. Okay, so what is the stable and unstable, or in fact neutral? How do you characterize stability or instability of a system like this, given the eigenvalues and eigenvectors of the matrix A that defines the linear system? What's the how do you? So if I perturb the system, I want to understand whether it's, so if I look at a solution, so okay, I guess I didn't even define stability. Should I? Okay, the definition of stability. I don't know where to write it. I will write it here. Something. A solution x of a fixed point. Let me just say it in words. If a fixed point is stable, if small perturbations of around a fixed point lead to solutions which do not go away from that fixed point, that they stay nearby the fixed point. They need not approach. If they actually, as t goes to infinity, approach the fixed point, then it's an asymptotically stable fixed point. Otherwise, it's just a stable fixed point. Mathematical details can be filled in, or look, I will give the reference of how to fill it. Okay, how do you characterize the stability of this using the eigenvalues and eigenvectors of this? When will this system be stable? When will this system be unstable? Negative, in this case, the real part of the eigenvalue. Yes, so negative something, but negative in particular, real part. This can be positive or negative, doesn't matter. It's a real part that decides the stability of the eigensystem. Yeah. Okay. So that leads to, and I hope this is something that you have studied. Multiple examples of this, at least in 1 and 2 dimension. 1 dimension is straightforward. If this is 1 dimensional, of course, there are no complex eigenvalues in 1 dimension. It's going to be all real eigenvalue because it's just the matrix itself is the eigenvalue. And in that case, if A is positive, the solution is always e to the power at times x naught. If A is positive, that goes to infinity. And if A is negative, that goes to 0. 0 is the stable or unstable fixed point depending on whether the sign of A is negative or positive. Okay. That defines the following objects. So ES is equal to the span of UI VI for I such that AI is less than 0. So take all the eigenvalues with negative real part, the corresponding eigenvectors of the matrix A, and the span of all those eigenvectors defines a space called ES, and that will actually refer to stable eventually. So let me write down the other two before stating what these are. So this is span of the same thing with AI greater than 0. So the U unstable is for AI positive, and the neutral or center actually is a better name for this, which is EC is the same thing, but with AI equal to 0. Right? So the fact, which is what I'm not going to prove, is that these are invariant subspaces That is, if x naught belongs to E star, then x of t equal to e to the power at x naught also belongs to E star. The star can be U or S or C. So for each of these subspaces, if you start with the initial condition in that subspace, the solution remains in that subspace. So that's what I mean by invariant subspaces. And in particular, for initial conditions in ES, the solution will approach 0. For initial conditions as t goes to infinity, for initial conditions in EU, it will approach infinity as t goes to infinity, and vice versa for t goes to negative infinity. And you really cannot say anything about what will happen to EC without knowing what B's are. Okay, so the EC is always the problematic case for talking about stability. If you don't have EC, these are what are called hyperbolic systems, and they have nice properties and so on and so forth. So, okay, should I write this down? Yes, I think it's a good idea to write this down, which is that at least I will write down for one of the two, and for let's say ES, and EC will be, sorry, EU will be exactly the opposite, switching the sign of time. Yeah. Actually, let me fit it here. If x naught belongs to ES, then the 0 as t goes to infinity and approaches infinity as t goes to negative infinity. So that's what we mean by stable, right? You start with the initial condition, as t goes forward in time, the solution approaches 0. And in fact, it has the additional property that it approaches infinity as t goes to negative infinity because it's a linear system, but that's just an additional bit. And you simply switch the signs of t for initial conditions in EU. So similar statement for EU. So t goes to minus t for EU. In quotes, because now you have to fill up the details of what I mean by t goes to negative infinity, negative t, but anyway, I hope you see. And there is in fact additional property that this happens exponentially. And this is exponential. The approach to 0 and approach to infinity both are exponential in time. Okay. Question? Sorry, say it again. Not for homogeneous autonomous linear system. It's this. For non-homogeneous systems, it's maybe, but not for this system. Yeah? Is that clear? Or is that obvious? Okay, so let's do it by contradiction. Suppose, sorry, question? Yeah, okay. Yes, but it will go to 0. It will go to, the perturbation will go to 0 in this case. No. Not delta x of t. This solution, x of t, e to the power at times x naught, that goes to 0. If you want to, okay, fine. So suppose, maybe, okay, here it's a, so let me draw a picture. I guess maybe the confusion is because I'm talking only of subspaces of this system. So here is, let's see if this picture helps or not. If it confuses more, then forget it. But so this is the fixed point 0. And I have a stable subspace. So this is my representation of ES. And then an unstable subspace, EU. These are orthogonal to each other. I can't draw too many orthogonal subspaces in high dimension, so that's why I have drawn this as some triangles. Actually, this comes from the book that is called Analysis, Manifolds, and Physics by three authors. I don't remember the full names. One is Cecil DeWitt, but anyway. So, and I haven't drawn the EC here at all. So if you think of this as the fixed point, and there is a perturbation, and I take a perturbation to be in ES. So now this is my initial. So if you want to call it delta x, sure, why not? Fine, I'll delta x naught. A perturbation delta x naught. Then the solution will approach 0 as time t goes to infinity, and will go up to infinity as time t goes to negative infinity. And so the solution, I should draw an arrow of time so that it's like this. And if it were to start in a different, if I should have drawn this with red color, but anyway, and if the delta x, not the perturbation, is in the unstable subspace, then it approaches this as t goes to negative infinity and goes off to infinity as t goes to positive infinity. That's what this statement says. I'm just not using the symbol delta x naught, but okay. So that's the real basis of stability. What happens for nonlinear systems, and what happens, in fact, for non-autonomous systems? Here is a fact that suppose you have a non-autonomous system, so the autonomous bit here was extremely important. For the non-autonomous system, so I'll just put it here because I'm not going to give the example, but if the system were x dot equal to a of t times x, then the eigenvalues, of course, the eigenvalues of a will be time dependent. Eigenvalues of A do not determine the stability of the system necessarily. Sometimes they may, sometimes they may not. That is, I don't have the example here with me. Or it's probably there somewhere, but anyway. There are examples of system where eigenvalues of A are negative have negative real parts for all times, but the system is not stable. So only the eigenvalues of A, behavior of eigenvalues of A, that is, they remaining with negative real parts for all times, is not sufficient to determine the stability of the system. And so that it's more complicated for non-autonomous systems, and hence it is also more complicated for non-linear systems. This is only for linear systems. So what do we do for non-linear systems? Take a break or continue for 10 more minutes? Should I continue for 10 minutes and then, okay. Sorry, take a break, meaning I'll take a break and then start tomorrow. I'm not going to start after the break, but.
Yeah.
10 minutes? 10 minutes is fine? Or should I stop?
Whatever you like.
Okay, let me just quickly do the nonlinear system. How do we relate the results of the linear system to nonlinear system? And that's roughly what we will start off by doing numerical simulations. So how many of you have solved ordinary differential equation, let's say Lorentz equations or some such appropriate system, ODE, linear or nonlinear, whichever one, using Python? For example, either Runge-Kutta method, RK4, that's one of the most commonly used methods. If not RK4, Euler method, for example, of solving differential equations, or some appropriate numerical. Okay, mostly with probability 1, I can assume that you know. Okay, if you haven't, please take a look at how to solve differential equations, in particular in Python, because that's what I will use, but if you want to use something else, that's fine with me. So how do we relate this to nonlinear systems? Very quick. What do you mean by time evolution of the perturbation of a nonlinear system? In this case, a perturbation, so the system evolves linearly, a perturbation also evolves linearly. What do I mean by that? I want to keep this in the linear part of the blackboard. So let me just put it here. If x dot is equal to a of x, then x dot plus delta x dot is equal to a of x plus delta x. And essentially that and that cancels. And so delta x dot is equal to a of delta x. So the perturbations behave exactly the same way as the original system. That does not happen for nonlinear systems, right? And that's the main difference. And that's where you get the following, which is that for a nonlinear system, I will consider autonomous nonlinear systems just to keep things slightly simpler in notation and so on and so forth. And anyway, the numerical simulations will be for all autonomous systems. The linearization I will write this as y dot equal to f of x y, where and f of x is the Jacobian df dx. This is a matrix. This is a what did I use? N. So this is in Rn. So this is a n cross n Jacobian of f, and the linearization is the time evolution, gives the time evolution of the perturbation. Gives the time evolution of the perturbation. And this is where the problem starts. That is, this is where now we go back to this, that the equation, the linearization is basically a linear equation, but non-autonomous. Why? F is a function of x. X is a solution of a nonlinear system, which is time dependent. So we can define A of t to be equal to f of x of t is non-autonomous. Or what I mean is really y dot equal to a of t times y is a non-autonomous linear differential equation. And the stability of a solution x of t or a fixed point, okay, if x of t is a fixed point, sorry, if x naught is a fixed point of the non-linear equation, then clearly this is autonomous, right? If x of t is x naught, a fixed point, then a of t is equal to a, which is f of x naught. So in that case, it's not, it is still autonomous, and hence, again, the stability of a fixed point is purely determined by the real parts, is the real part here, of the eigenvalues of the Jacobian at the fixed point. It's exactly this autonomous linear dynamical system result. But for solutions which are not necessarily the fixed points, that is actual time-dependent solutions of the dynamical system, the stability is determined by this non-autonomous dynamical system, and hence only the eigenvalues of the matrix A or the Jacobian F do not determine the stability of the system. And that's why we need to talk about Lyapunov exponents. And that's that's one of the reasons why Lyapunov exponents are not the eigenvalues of the Jacobian or In fact, there is no obvious, easy, or in fact, as far as I know, any relation that you can write down between the eigenvalues of the Jacobian as a function of time and the Lyapunov exponent, except in one dimension, of course, but one dimension is special. Okay, so what are the Lyapunov exponents? Well, maybe I will just at least define what the Lyapunov exponent will be. So if okay, no, yeah, two minutes. So if E1 through En are standard unit vectors, so these are just, so EI is 0, 0, 1, 0. And this is at the ith. So EK, this is at the kth location. Then with is basically gives the time evolution of all possible perturbations of the system in terms of, in the sense that these are all possible orthonormal directions of perturbations of a dynamical system, and a matrix that time evolves each of these perturbations and then just put together into a matrix basically gives the time evolution of the perturbations of the system, and that is what is eventually used to define the Lyapunov exponents. So then consider, I should say consider, so this is just a linear dynamical system, linear differential equation. Linear differential equation, it's linear in M, it's not linear in X. So the original system is nonlinear, so it's a nonlinear linear system in M. And the behavior of eigenvalues of M as t goes to infinity, so to say, essentially determines, well, okay, in a very vague sense, this is not a very precise statement, but so the Lyapunov exponents are basically and it's like the last bit, which is are the eigenvalues of the following matrix. Limit t goes to infinity, m of t, m star of t, to the power 1 over t. Actually, maybe I'll just do this for real cases, so 1 over t. Yeah? Motivation for this is going to take a bit of a time. It's not so straightforward. As I said, the eigenvalues of A do not determine the behavior. So what is it that actually determines the stability behavior of the solutions x of t? It just happens to be this complicated object. There is no simple way around it. That is it. And I can't reduce the complexity to less than that. But anyway, so okay, motivation and all that, we are missing bits, large bits and pieces, how to get to motivate this, but not enough time right now. Maybe tomorrow we'll start with that, and then. Okay, so please bring the laptops tomorrow, and we can play around with how to compute the eigenvalues, and the eigenvectors of these are what are called Lyapunov vectors. So these are Lyapunov exponents and eigenvectors. Well, okay, are Lyapunov vectors. I'm putting things under the rug a little bit. So anyway, so there is backward and forward Lyapunov vectors, and we'll discuss those details maybe later. But okay. Okay, and that's what determines the stability. Instead of the eigenvectors and the eigenvalues of the matrix of an autonomous system, you really need to build this significantly more complicated object and its eigenvectors and eigenvalues in order to talk about stability of these systems. Okay, okay, I'll stop here. Swamped? Too much, too many things in too short a time, possibly? But, well, sorry, I guess.